Okay, we're going to go ahead and start with our lesson on thermodynamics. We have finished up kind of the heat transfer part of our thermo unit. Do a little bit of review first. Remember temperature, quickly through this. Temperature is a measure of hotness, average translational kinetic energy of molecules, so not necessarily related to potential energy of molecules or rotational energy, but just the average translational. We have our relationship here, Ke average, 1/2 mv squared is 3/2 kT. K is the Boltzmann constant, and T is absolute temperature in Kelvin. So these are relationships we played around with before. Then we started talking about internal energy. Internal energy is the sum of all energies. So translational, rotational, potential, all of that is packaged into your internal energy. If you have more material, or the mass of material, you're going to have more energy stored. And finally, you can increase your internal energy by raising your temperature or adding more material. We're going to find out one new way to add the increase in temperature as well, or soon. Okay, so we talked about moving energy around. The method we do that is using heat. Heat is a form of energy in joules. It will flow if you have a difference in temperature, so a temperature gradient. It will go from hot to cold. And it's going to keep flowing until you reach some sort of equilibrium. So if heat is added, an object is going to do one of a couple of things. It will warm up, which will increase its temperature and internal energy. The amount of temperature increases depends on its specific heat capacity. So with a really high specific heat, like water, if you add heat, it won't change the temperature very much. But if it's a low specific heat capacity, it'll change the temperature a lot. If something is undergoing a phase change, then adding heat will cause it to do that phase change based on the amount of latent heat that is stored for that particular type of material. 3 forms of heat transfer: conduction, convection, radiation. So let's talk about each of those. Conduction, remember, requires a medium. Best conductors have molecules that can move while in close proximity. So metals are really good conductors because the electrons can move around. The energy transfers, but the material itself sort of stays put. Poor conductors we call insulators, and a hot fork is an example. You put a fork into a burning flame, it will quickly heat up and burn your fingers. Convection is the other form. It relies on a flow of matter. So in this case, the matter actually does move, so it has to be a gas or a liquid where the density can vary. And when the density varies, then you're going to get an upflow. So hot air or fluid tends to rise, which can set up a convective current where the hot air rises and it's replaced with colder air or fluid, and it can create these cycles. And it is the convective currents on our Earth that create all of our weather patterns. Forced convection is when you blow something over something that's warm, causing some convection, but it would necessarily, it kind of makes it happen a little faster than if you just have it convect itself and have the air rise because it's less dense. By putting your hand above a candle, that would create, that is a form of convection. That's why you burn your hand. And finally, we had radiation. Radiation does not require any medium. Heat is going to radiate from a source. So the sun radiates, a flame does, so does your skin. Basically, everything both absorbs heat and radiates heat. The form of heat transfer in this case is a form of electromagnetic radiation. It is in the infrared spectrum. Part of the light. So if it gets white hot, though, then it would be in the visible spectrum, but most of heat is radiated in the infrared. Everything both absorbs and emits radiation. Some things are better than others, and the things that are better than others, or best, are called black bodies, and they have an emissivity of 1.0. The rate of transfer of heat when you're talking about radiation is going to be proportional. It's more complicated than this, but generally speaking, it's proportional to the emissivity. So it's a black body, it's going to emit really well, times the absolute temperature raised to the 4th power. So the transfer of heat is strongly correlated to the temperature. In other words, high temperatures are going to radiate heat really well. Okay. So we've talked about conservation of energy. Remember the roller coaster scenario. We say in a closed system, the change in kinetic energy and potential energy and internal energy is going to be equal to 0. Closed system just means you're not adding heat or letting heat escape. So we can rewrite it to say that the initial energy is the same as the final energy. That's conservation of energy. In a frictionless world, then we'd say that that these two things go away. You don't have a change in internal energy. So we say mechanical energy is conserved, which is just kinetic and potential. But most cases we do have friction, so the total energy is conserved, which would include internal energy as an object heats up. But what affects the change in internal energy? To increase in temperature and thus the internal energy, you're going to have to add some heat. To decrease the temperature, you could remove heat. To increase the temperature, you could also do work on the system. So this is kind of a new concept. It makes sense if you add heat, it's going to increase internal energy. But now we're going to talk about also doing work on a system will also give you a change in internal energy. Think about compressing something, and as you quickly compress it, it will warm up. It's going to be changing its internal energy. Even you didn't add heat to it, it can still do that. You can also decrease the system's temperature by having the system do work. And that's kind of the idea of thermodynamics. So thermodynamics, we define it as thermo represents heat, dynamics represents moving. So remember F equals ma, we talked about that was the study of dynamics when we had kinematics types of problems. Thermodynamics is the study of heat and its transformation into mechanical energy. The steam engine was first invented in 1698. Thomas Savery was the inventor of the first steam engine. The Watt steam engine, which was a better version and was the dominant design that led to our Industrial Revolution, 1769. So remember, James Prescott Joule was the first one to kind of take the mechanical equivalent of heat, in other words, taking mechanical energy and converting it into heat. But well before that, the inventors had understood that if we can use heat, we could create an engine and generate mechanical work. And that is really, really useful, because then we don't have to use horses and men and women to lift things and push things. So you can use a machine to do it instead. Quick review of work. Remember, force parallel to direction of motion, so FD cosine theta. It is the component of force that is in the direction of displacement. It has units of joules, so it's an energy unit. Quick review of pressure. Pressure is defined as force per unit area in a direction perpendicular to the surface. So the units for pressure are going to be newtons, that's force, over meters squared, that's area. And we call it in SI units the Pascal. So 1 Pascal is about the pressure of a dollar bill resting on a table. So 1 Pascal is a very, very small unit of pressure. Typically we'll talk about things in kilopascals. Think about this scenario here. If you have an upright book, they both have the same mass, or they're going to have the same force acting on the table, but one has a smaller area, so it's going to have more pressure. So pressure is force per area, or pressure is force per area, or force is pressure times area. It's helpful to be able to think about those both ways. Okay, so the SI unit for pressure is a Pascal. Other common units you'll see are pounds per square inch, or PSI, like when you pump up your basketball, you have to do it to a certain PSI, or your car tire. An atmosphere is another form of pressure that we use commonly, and you will need to remember this conversion. Not remember it, it's on your formula sheet, but 101,325 Pascal is 1 atmosphere. That is essentially the atmosphere here at sea level, due to all of the atmosphere that we have up and above us kind of pushing down on us. So as gas particles bump into the walls of a container, think about our momentum, right? F delta T equals M delta V. As they bump in, they change the momentum. There must be a force there. If you have lots of particles, you get lots of force, and that's what creates pressure. Okay, so here's your first corny physics joke. Einstein, Newton, and Pascal are playing hide and seek. Einstein starts counting, and Pascal runs upstairs to hide. Newton thinks for a moment, pulls a piece of chalk from his pocket, draws a square on the floor, each side 1 meter in length. Einstein stops counting, opens his eyes to find Newton stood right there, standing in the middle of the square drawn on the floor. Ah, Newton, I found you. Incorrect, sir. You found 1 Newton per square meter. You found Pascal. Ha, 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 ha. Okay, a thermodynamic system. We want to define a system as having stuff basically on the inside and then stuff on the outside, and we have a boundary that separates the two. We're going to talk about typically like quantities of gas or a fluid, so some gas inside of a piston. That would be considered your system, and then your outside would be your surroundings. So when we're looking at a gas piston, this is something we typically think about in thermodynamic system. You have a gas here, and you have a cylinder, and there's little gas particles inside, and you have this piston that can slide up or slide down. You can pull it up or pull it down. We say inside the piston has a certain volume. So by lifting the piston up, you have just increased the volume. You've increased this distance right here. And this graphic's trying to show you that by heating the piston, you've increased the pressure, and the pressure increase pushes up on the piston, increasing its volume. Okay, so that's sort of the scenario going here. You have a piston, then you heat it up, and then it expands. So if we look at the math going on, we have pressures, force per area. Work, remember, is force times distance, but we just talked about how force is pressure times area. So work is going to be pressure times area times distance. But area times distance is the change in volume. So it turns out that work is equal to P delta V, as long as the pressure is constant. Okay, so for a constant pressure thermodynamic process, we're going to talk about a whole bunch of different types of processes. For a constant pressure process, we say work is equal to P delta V. For a more complex type of scenario, you'd have like work is the integral of P dV. Okay, so we're going to keep it simple and say that the pressure is constant, and then this integral becomes a lot easier. And that was super messy anyway. Okay, so keeping it simple here. When we're talking about thermodynamic processes, the signs are really important. You have to be really careful. So what we say, our kind of definition is when work is done by a gas on a piston. Okay, so in other words, the gas pushes up on the piston and causes it to move. The piston expands. We say delta V is positive. So the change in volume is positive, it's increasing, and the work is also positive. Think about delta V. Delta V is V final minus V initial. And if you have a big V and you started with a little v, then that's going to be a positive number. Positive number. Okay? So as a piston expands, it's doing work on the environment. We say that both the work is positive and the change in volume is positive. If a piston is compressed, so it gets smaller, if the press gets smaller, then we're saying that the delta V is negative and the work is negative as well. In other words, work is being done on the system. So if you're doing work on the system by pushing the piston down, then we call that a negative work. So when the piston itself does work, that would be positive, but when you do work on the piston, that would be negative. Okay, we'll give you some examples here in a minute. Find the work done by a sample of gas if it is compressed from 25 liters to 15 liters at a constant pressure of 2.0 times 10 to the 5th Pascal. Okay, so since we have a situation where we have constant pressure and a compression, we know that the work is going to be equal to P delta V. So P is going to be 2.0 times 10 to the 5th Pascal. The final volume is 15 liters and the initial volume is 25 liters. So we know W equals P delta V in a constant pressure situation. So pressure 2.0 times 10 to the 5th, that's going to be Newton per meter squared, remember that's a Pascal, times 15 liter minus 25 liter, and that will help us find our work. Now here's the problem. Your pressure is in Newton per meter squared, your volume is in liters, and those are not related. So you're going to have to convert liters into meters cubed. Now fortunately that conversion factor is on your formula sheet at the very top, and it says 1 liter is 0.001 meter cubed. So you can convert from meters cubed to liters, or liters to meters cubed, and then go ahead and multiply this out, and you'll find a total of negative 2,000 Newton meter, which is the same as a joule. And that makes sense because we're talking about work, which is a form of energy. Notice it's negative because our volume became less, right? So because we have less volume, that means there has been a compression done, which means that there has been work done on the system, which makes it negative. Okay. There we go. Okay, so energy types and thermodynamic types of problems. We can have heat added to a system, we can have work done by a system, and then we can have internal energy changes. And it's sort of like a bank account where you add money and then you can increase the amount of savings that you have, and you can have money to spend. By changing one, you're going to affect the others. The idea is we're going to think about different processes that will allow one type of change and see how they affect the others. So our analogy again is, let's say you have a bank deposit, okay? Bank deposit, that's going to be like having heat. So if you add heat, well, I don't know why it writes so weird right now. If you add heat to a system, then you could have a change in internal energy, okay? So you could increase the internal energy, or you could spend some of the energy by having work done. Okay, so by adding heat, you could increase energy or have work, or some combination of the two. Okay, and there we go. Got it right out there for you. Okay, so first law of thermodynamics is basically another expression of the conservation of energy. We call it the first law. We'll talk about the second law in a couple days. It is basically conservation of energy, but now we're going to be including heat. We know that energy cannot be created or destroyed. And then here is an expression that is typically seen, this is the type you'll see in your textbook, this is the type you'll see in many textbooks, which is the change of internal energy is equal to the heat added minus the work done out by the system. This way of depicting it, remember I've just moved things around. I moved Q to one side and delta U to the other side. This is exactly the same equation, just rewritten, but this is our bank analogy where you add heat and then you're going to change the internal energy or be able to spend that energy in doing work on your environment. So that's like your checking account. Okay. But delta U equals Q minus W. That's the typical way we write the first law of thermodynamics. Most processes are going to involve some sort of change in either heat or work and internal energy, or maybe some multiples of all of them. Some we will talk about isolating and saying, okay, well, if we do a simplified process, then what will be the effect? So we talk about several different types of these special processes. You use the word iso. So iso means it's equal or it's constant or it's the same. It's going to be held constant as we're describing different types of thermodynamic process. So for example, an isobaric process, think baric like barometer. An isobaric process is a process that has constant pressure. And we just observed an isobaric process where we had a piston that was being compressed at constant pressure. So what happens to our first law of thermodynamics when we have an isobaric process? First of all, we know that we can use work is equal to P delta V. So that is useful to know. You could have an isovolumetric process. That means you have the same volume. So think about a container that is full of gas, and you can't compress it or expand it, but you could heat it up. Okay, so that would be an isovolumetric type of process. In an isovolumetric process, because there isn't any kind of compression, delta V is going to be 0, you can't have any work done. So in isovolumetric, you say there is no work. An isothermal is called a constant temperature process. In an isothermal process, you need a great big heat reservoir. That just means like a bunch of material that's all at the same temperature. And we'll give you some examples here coming along, but I just need you to know that up front. In an isothermal process, then delta U is going to be equal to 0. You cannot have a change in temperature if everything is done at constant temperature. So if there's no change in temperature, you're not going to have a change in internal energy. And then finally, we have an adiabatic process, and this is the one that has a weird word. There's no iso in it. An adiabatic process is a process where no heat is added or lost during a compression or expansion. So think like thermos. When you have a thermos and you do some sort of a process, then heat is not allowed to push in or escape. Okay, so often when you take a piston and you squeeze it really fast, then you could do an adiabatic process. It's not a constant pressure process, but it happens so fast that heat is not allowed to escape. In that case, we say that Q is equal to 0. So in each of these four types of processes, we have special considerations that allow us to think about solving problems with the first law of thermodynamics. An example, try this. Pucker your lips, and if you, I should say, put your hand in front of you and open your mouth nice and wide and blow on your hand, and it's going to feel nice and warm. But if you pucker your lips and then blow, it's going to feel really cool. That's what we call an adiabatic expansion. It goes from high pressure inside your mouth to low pressure outside your mouth, and in that process, as it goes from high to low pressure, it cools. So we call that an adiabatic expansion. Another example we've talked about with these fires is an adiabatic process where you have air that starts off at a high altitude, and as that air is pushed with the wind and it comes down to a low altitude, it heats up. We call this a Chinook wind when it goes over the Rocky Mountains and goes into Colorado. In California, we call it a Santa Ana wind, and more recently, we have what we call the Diablo winds, which is basically the Northern California version of a Diablo wind, and that's the wind that comes from the north and basically the northeast and blows in the westerly direction. That is the wind that set off the Paradise Fire. We had really dry conditions. You had air that was moving in the western direction, and as that air went from a higher altitude to a lower altitude, it was compressed, causing it to heat up, and then all that dry foliage just was tinderbox, and it just exploded and caused that devastating fire. So that is considered an adiabatic process because as it goes from low pressure up here to high pressure down here, Q, there's no heat allowed to come in or out, and yet the internal energy increases dramatically. Okay. We'll demonstrate as well as class some of these things for you too. But a gas is rapidly compressed adiabatically. The temperature of the gas will. Hopefully you can remember from chemistry, if you put a lot of pressure on something really quickly, then the temperature of the gas is going to increase. An ideal gas undergoes an isothermal expansion. Q is what? So isothermal means what? It means constant temperature. So if something is going to undergo an expansion, that stays at the same temperature. So think about a piston that starts at this level and goes to a bigger level. In order for it to expand, I will have needed to increase the pressure. And in order to increase the pressure, I will have needed to have added heat. So an isothermal expansion, even though it could be at the same temperature, Q is got to be positive. That might seem counterintuitive because you think if there's a flame, how could it be isothermal? The idea is that you're going to really slowly add heat, and the heat is going to change the pressure, but not the temperature. And by changing the pressure, you're going to be doing work with the piston. Anyway, okay, so keep going. So thermal process delta U is equal to Q minus W. How do each of these processes translate in terms of this equation? So an isovolumetric process, remember, in an isovolumetric process, you have a constant volume. That means you're not going to have any work, right? Because there's no P delta V. The volume can't change. So this equation is going to change to say delta U is equal to Q minus W, or just delta U is equal to Q. If you have an isothermal process, that means constant temperature, then delta U is going to equal 0. So delta 0 is equals Q minus W, or Q equals W. So the amount of heat added is going to translate directly into the amount of work that you can get out. An adiabatic process, we say no heat is added or lost, so think about what happens to the equation here. If there's no heat, then we're just going to get Q is equal to delta U is equal to 0 minus W, which is just negative W. So let's try an example problem. If the change in internal energy of a system is 350 joules, when 750 joules of heat is transferred to it, find the work done by the system. Okay, well, first law of thermodynamics says that delta U equals Q minus W. We know we're given that, oops, that was weird. We're given that we have 350 joules change in internal energy, so we'd say delta U is equal to 350 joules. It's positive. 750 joules of heat is transferred to it. So you're adding heat. It's like adding money to your bank account. 350 joules goes to change the internal energy. Well, where does the rest go? So 750 joules for the heat. Set up your equation. 350 joules equals 750 joules minus work. Solve for W, and you get 400 joules. Okay, and notice that number is positive. So that's the amount of work done on the system. I'm just going to express it in our bank account scenario. Remember, which was Q equals delta U plus W. Okay, so if you put in 750 joules, then you're going to get 350 of U and 400 of work. Okay, so you take a deposit, some of it goes to savings and the rest goes to your checking account or spending it. You're spending that work. Okay, and there we go. Gas undergoes an isovolumetric process. Which of the following is going to be larger? Okay, take just a second to think about that. Which one is going to be larger? Q, delta U, or they are the same? Take a guess, all right? Okay, so let's think about what's going on. We have delta U is equal to Q minus W. When you have an isovolumetric process, then we say that work is equal to 0 because the change in volume. There's no P delta V because delta V doesn't change. So we say the work is 0, and if the work is 0, that term goes away, and you get just delta U equals Q, which means that they are the same. Okay, and that concludes our thermodynamics lecture. Go ahead and give it a try with the homework problems, and we will follow up with some demos in class.